the title, so it's going to show up as stats. But the image, it'll say calculus, in the thumbnail, but whatever. Okay, so those who are just joining us, we're changing the test day, and I'll fix attendance, Daniel. You won't be absent. I think I marked you absent. So before we started, I was told that this is something we need to look at, and I've got a few that I wanted to look at as well from the homework, because I didn't know how things would go. And so today is sort of a catch-up day of sorts, and some new stuff. The next homework, by the way, will not be due until Wednesday. It's not even online yet, but it's going to be about the comparison tests. More on that in a bit. First, we need to deal with sort of picking up the pieces from this integral test. So, and when I approach this, the function that we're dealing with here is 1 over n to the 0.999. Now, there's two ways that we could do this. So I'll do it both ways because we need to talk about both of them. One of them is the integral test. And the other one is, well, we'll get to that in a sec. So the integral test just says that if f of x is decreasing and positive, then the integral from maybe 1 to infinity of f of x dx and the summation, n goes from 1 to infinity of f of n, will share the same fate. So what I mean by that, or what mathematicians mean by that, is you probably figured out, is that if this one converges, then this one will, and vice versa. They share the same fate. If one converges, the other one will. If one diverges, the other one will. So we use that. The way we use that is we say, okay, it's too hard to think of adding together all of these terms. And so instead of dealing with this, because this sequence is a decreasing function, we're going to use this. The integral from 1 to infinity of 1 over x to the 0.9999. Well, that's an easy integral to do. Let's see, this is, I'm going to forego, no, I won't. I'll write it as a limit. As b approaches infinity, it's painful, I know. Of this, let's do the antiderivative of x to the negative 0.999 will be 1 over 0.0001 x to the 0.0001. Evaluated from x equals 1 to x equals b. So far, so good. You probably did something similar, I hope. So there's my antiderivative. And I know that's such a small number. It shouldn't matter, should it? Well, it does. You pick, so here's the deal, is that you do this, you do the limit as b approaches infinity of this, let's see, b to the 0.0001 over 0.0001 minus, sorry. Well, I guess I could have, yeah, I'll just leave it there. 10,000? Isn't that what 1 over 0.0001 is? Let's see, hundredths, thousandths, 10,000ths. Yeah, that's 1 over 10,000. Or this number is 10,000. I could have done the same thing here. So this exponent, it seems so small. Like it doesn't really matter, does it? Well, it does, because you put big numbers in here. Say you put 1 billion in here, you get like 10. I don't know. What's the, let me see, where's a calculator? What is the 1 billion? Just a minute, I'll do this. 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. There's 1 billion to the 0.123 zeros and a 1. Oh, it's only, I was wrong. I was off by a huge amount. 1.002. It's so small, right? But the deal is that just keeps growing. I know it's such a small, let's do, well, I guess what we would have to do is raise this like 10 to the 100th power or 10 to the millionth power. It'll be, you're going to have to pick a b that's really, really big. But eventually, this becomes so big, it diverges. So even though that number is really small, this does diverge. Diverge. And because that diverges, this will diverge. So this diverges. Put a big D there, put a box around it, we're happy. Okay, so that's the hard way to do this. The easy way, hopefully you caught this. If not, we're doing it now. So that is that this is a P series. P series, oh yeah, okay, Hayden, what's going on?
How do you get the 10,000?
Okay, whoops, I guess I'll do it here. 1 over 0.0001 is 10,000. Is it not? Am I off? Here, I'll do it on my calculator to make sure. Yeah, so I plugged the lower limit in, the 1, into this. Yeah, because that 1 to this power is just 1. Let me do this. 1, 0.0001. Yeah, 10,000. That's it. Yeah, decimals are weird. You're right. But we love them. Okay, so P series. So a P series, here's the rule, is that if you have a sum of 1 over n to some power, that's why this is called a P series. That power matters that this thing will do one of two things. It will either converge or diverge. So it converges when P is greater than 1, and it diverges when P is less than or equal to 1. You might say, what happens when P is negative? Diverges. So as long as P is less than or equal to 1. So this means, oh yeah, what do you think, America? No, this is P. Because, well, think about it. If you have something like, let's say P is equal to -2. So wait, whoops, get rid of this. Okay, so let's say that P, so you have 1 over n, let's do this, to the -2 power. If you used absolute values, then this should converge, but this is the same as the sum of n squared. Clearly diverges, because it gets bigger and bigger. Yeah, so here, P series, which I know it's annoying to have different rules, but this is going to be this is your fate for the rest of the semester, is being confused by, is this rule mean absolute value or what? So we'll sort it out. That's why I have this over here ready to go. So we're going to sort it out, hopefully. And hopefully it'll make sense. Okay, so P series converges when P is greater than 1, diverges when P is less than or equal to 1. So, well, what's the value of P here? P is 0.999, less than or equal to 1, diverges, done. So that's going to be our very first rule on our flow chart. But I need to mention one more thing about this, is that there is a special series. So this one's special. And that's when P equals 1, you have 1 over n. And this one diverges as well, but we have a name for it. That's the only reason why I'm going to sort this, make it like kind of orange. And this is called the harmonic series. So this is the harmonic series. And this diverges. But because this pops up in different places, if I say harmonic series, hopefully if you don't remember what it is, don't fret. Just say, hey, what was the harmonic series? I'll say, oh yeah, it's this one. So it's kind of like the edge case, like between, notice that when P is greater than 1, you converge. When P is less than or equal to 1, you diverge. And so this is like the edge in between. Okay, let's go on. So that was that. So I've got these written on here because I knew that they would be issues. So we'll come to those in a bit. But I want to see if there's anything else from the homework that I'm forgetting about, that we need to take a look at. So is there anything else that we need to look at before those last three, 38, 39, and 40? So it wasn't terrible, was it? Hopefully, you're doing integrals. Yeah, it's infinite, whatever. Okay, let's take a look at these last three. and see what they are. So let's do these in reverse order. Actually, we'll do 40, and then we'll see if we need to do either of the others. Give me a second. I typed them up, but I didn't. I think I'll feel better if I put this over in Notability. So give me a sec here. Where should I put it? Put it down here. Okay. Okay, we'll do number 40, and then we'll come back to the others if need be. So, I believe my typing is poor. This is all in the denominator? Yeah, I think everything there is in the denominator. So, yeah, it's just I think this is sort of the way it was written in the book. So let me do a better job. 1 over n times the natural log squared. Okay, so we want to be able to use the integral test. So that's what we're going to first of all do this. We're going to name our function. The function is this. That's kind of nasty, isn't it? So we need to know, is this decreasing? Decreasing. Oops, there we go. Because if it's not a decreasing function, also is it positive? So we have to check these. And I don't remember what I did in the videos, because I think I put videos from the pandemic up there. Anyways, I forget what I did then. But I don't know if I checked this, but you got to check it. You got to check it. At least give lip service to it. So are these positive? By positive, I mean if you plug in n equals 2, any number bigger than 2, you will always get a positive number, right? Those are always positive. That's always positive. So yes, this is always positive. Check. Is it decreasing? Well, that's hard, but one thing you could do is you could graph the function. There's another way to check to see if you're always decreasing, and that is to do the derivative. So there's different ways to do this. I'm going to cheat because I don't want to have to do the derivative of this thing, because it's going to involve the product rule. But if so one way you could do this is you could do the derivative, and is the derivative always less than 0? That's sort of one way to do this. I'm going to cheat and use my calculator. So if you don't know how, you press the y equals button, and you get 1 over, in parentheses, we have x times, in parentheses, natural log of x. And then I'm going to square that. I'll put it up on the screen in just a second. I think I've got everything here. Whatever, let's graph this and see what happens. Interesting, interesting. It's interesting. Let me, just a minute, change the window really quick. Okay, that's going to be better. Okay, here we are. This is interesting. Let's see, can I get a good photo of this? I don't know if I can. Add photo, take a picture. Yeah, look at that. That's beautiful. I know you can't see it yet, can you? That's all right. You'll see it soon. Okay, use that. Beautiful. Okay, so there's my here's my graph. Ugh, hard to see, isn't it? It's okay. So, but if you did this graph as well, you can see that the function itself is decreasing. So this is, whoops, this is 1. So here's x equals 1. Here's x equals 2. So from there over, you're decreasing. So this is certainly not a proof that you're decreasing. It's just because who knows what happens beyond the screen, but it's pretty good evidence, right? This thing is decreasing, and it's probably going to keep decreasing. So if we wanted to be sure, we would want to take the derivative and see if the derivative is less than 0. But let's not. I mean, I could, but let's move on. We don't have that much time. So, so since that's the case, we know we can apply the integral test, and so that's what we're going to do. Now, in terms of this statement, correct within that much, that is referring to the remainder. So let's do it this. Let me remind you of this in case you didn't catch it, is that if we do a sum, n equals 2 to infinity, whatever, of, let's call it a sub n, that's going to equal a partial sum, I'll use capital N, plus a remainder. So this is a partial sum, and this is the remainder, the error. So this r sub n, that's the error from chopping off and saying, I'm done, I'm not going to add up any more terms, I'm done here, let's not add up the rest. That is always, when you can use the integral test, this only works when this is true. So as long as those are both true, then you can say that the remainder will be less than or equal to the integral, starting at n and going to infinity of the function. So the way to think about this, if we're trying to be correct within 0.01, then we want this integral to be less than or equal to 0.01. And so here's how this is going to look. I'm going to have this integral up here. So this is the integral from n to infinity of 1 over x times natural log of x squared dx better be less than 0.01. And so I'm going to solve for capital N. So that's the job that you have, if you hadn't figured it out. Not hard, though. I hope you can see that this is an easy substitution problem. But in case you can't, I'll write down my substitution. U is equal to natural log. Du is 1 over x dx. And so this thing can be written like this. 1 over natural log of x, quantity squared, times 1 over x dx. And so this will become this. Integral of 1 over u squared du. Pause for a minute, make sure you're not lost. Anything? Problems? I know algebra is hard. Algebra is hard. But hopefully you can overcome that. Okay, so what's left here? We just have to do that antiderivative. We all know what that is. That's going to be negative 1 over u. You can, if it bothers you, you could write that as u to the negative 2. Add 1 to negative 2 and you get negative 1. Divide by negative 1. I know it doesn't look quite the same, but it's the same thing. Then we'll go back to x, and we get negative 1 over the natural log of x, evaluated from n to infinity, should be less than 0.01. So just pause for a minute and see what I've done here is I've taken this, I used substitution, I've got my antiderivative, which I've written here. Now I'm going to plug in my limits, and I'm going to cheat a little bit, and I'm not going to write a limit here, but you know what this is. That means do the limit as x approaches infinity of this, which we all know is going to be 0, but so this will be negative, well here, just 0. So the upper limit is 0 minus the lower limit, 1 over natural log of n. Has to be less than 0.01. So 1 over natural log of n is less than 0.01. And then that means that we can flip this baby, and it becomes greater than 100. So I just reciprocated both sides. So now I just need to know, well, what n will give me a natural log that's greater than 100? Well, let's change this to exponential form. Really? Seriously? That is not a happy number. That's huge. Surely that can't be the answer. Well, I guess I could look it up. I have the answer key for everything, but I'm curious to see e to the 100. That's huge. Let's see, e to the 100. Yeah, that's on the order of 10 to the 43rd. So you're going to be adding for a long time. That's ridiculous. How could that be? Did I make a mistake? Less than this. This is good. That is good. This is... I'll double check. Now I'm curious. I'll double check. Check me. I'll bring back a report. I'll bring back a report. Unless, did the AI overlords do this one for you? No? Okay, I don't know. Okay, they can't do this? They don't know calculus?
No.
Okay, I didn't know.
That's what I know, so.
Oh, you got e to the 100?
I hope it's right.
I hope so too. It just seems so big. I'm gonna check me anyway. Okay, onward, let's go back here and grab this thing. Let's see, get rid of my calculator. Can I delete? Yes, I can. Let's see, can I just paste in this thing again? Yeah. So I saw these three, and I thought those, if anything, those were probably and before class, someone asked me about number 40, so I thought, well, there we go. We've got number 40. But do I need to do another one of these, or is this, do you understand the process now? What do you think, Michael?
Does 38 involve the, integration by parts?
It certainly does.
Can you go over that one?
We certainly can. So here, I'll put this down here where we can enjoy it more. And then, yeah, so 38, because the answer to 39 is in the back of the book, so you can check your work with that one. But 38, there is no answer for the back of the book. So let's do 38. First of all, the function is x e to the negative 2x. And let's just assume for a moment that we've checked that this is decreasing. And once again, the way you would do this, if I were doing it correctly, I would do the derivative and make sure that the slope was always negative. So as long as the slope is negative, this is decreasing. But you can trust me, well, pretend that you can. And this is negative. Also, this is always positive. So the function values are always greater than 0, which is true because notice what you're plugging in. You're plugging in values of n starting at 1. So x will always be positive. Exponential functions are always positive, so the product will be positive. So let's just say that we've already checked that, positive. So here, just to emphasize, f of x is less than 0, and f prime, and f of x is greater than 0. So you're checking those are what you're checking. So let's just say that we've done that, and so I want this. I want the remainder, which is equal to this, to be less than 0.0001. That would be 4 decimal places, wouldn't it? So let's just go with that. So we need to do this antiderivative. U is equal to x, dv is equal to e to the negative 2x, dx is equal to dx, v is e to the negative 2x over negative 2, which I suppose you might have to use substitution to get this, but hopefully you're used to doing that. And then we'll put this together. So this is the integral of u dv is equal to u times v minus the integral of v du. Whoops, sorry, I will fix that. I messed up. I should have just used the eraser in the first place. Okay, oh come on, e to the negative 2x. There we go. So far so good? I'm tracking okay? So then let's just polish this off. This will equal, what is this, negative x e to the negative 2x over 2. And then the antiderivative of that thing is going to be negative e to the negative 2x over 4. So I know you're worried about my negatives because I am being extra negative here, aren't I? But there is a triple negative. I'll point out the negatives. Here's number 1. Here's number 2. Those cancel. But then when you do the antiderivative of e to the negative 2x, you get another negative. So that's why this is negative. Make sure you get them all there. Now I'm going to, let's do this. And I will cheat again and do the limit. Technically, I should be doing L'Hopital's rule with this one. But basically what you've got here is you have x in the numerator, e to the 2x in the denominator. E to the 2x is so bulky it dominates. The x is just, it's irrelevant. And then this, of course, is going to be 0. So both of those are 0. So the limit as x approaches infinity of that thing is 0. And then you plug in the n. So you have negative n e to the negative 2n over 2 minus e to the negative 2n over 4. And I want that to be less than 1 over 10,000. Now just a little bit of algebra, or I should say creative algebra. I'm not going to do this. Why would I do this? Well, here, let's see. I'll show you what I will do for you. So this will be 2n minus or plus 1 over 4 times e to the negative 2n. Okay, so just a little bit of algebra there. Not bad, though. All I did was I took care of all the negativity, so now we're finally positive again, negatives. So all of this is positive. And then here, I wanted to write it as a common denominator of 4, so I need 2 times n. And this is just one of these things. And then I pulled the e to the negative 2n out. That's all. Now I'm going to flip everything because I want to. I think it'll be easier for me. So 4e to the 2n over, you don't really have to, but it's just going to be easier for me, should be greater than 10,000. So now, honestly, at this point, to solve this because of the exponential and the n in the denominator, I can't solve it. So here's actually what I'm going to do, is I'm going to guess and check with my calculator. So give me a sec here. What I'm going to do is I'll do 4 times e. It's not going to be, I'm not going to have to guess and check much. Okay, so you might think, well, what? I'm going to start with n equals 5. Wait, 10,000, give me a sec. I'll start with n equals 6 and see where that puts me. N equals 6, that would be e to the 12th, 4 times e to the 12th, divided by 13. And I've got 50,078. So certainly n equals 6 is bigger than 10,000. What about n equals 5? Because I want to know the very first time that this is good. So when I do n equals 5, I get e to the 10th over 11. So 4 times e to the 10th over 11, and that gives me 8,000. So n equals 5 is a no. So in other words, when, how many of these do I need to add up? I just need to add up 6 of them. So n equals 6. Go to 6. 6 is the answer. So it's okay. It's okay to do this, especially when you know that the numbers are, like e to the 2n, that's a huge number. It's going to easily get bigger than 10,000 quickly. So I might as well just guess and check at that point. That's fine. All right, did that help, at least with number, whatever this is, 38? So we're ready to move on. We'll skip 39 because that's, but if you do have issues with that, we can do it later. Let's give it a try with this quiz. So just to warn you, let me look at this. This looks good. Yeah, this is all easy stuff. So these are all integral tests. So you're just going to apply the integral test. And I'll just tell you up front, just to save you the trouble, is all 3 of these satisfy the requirements of the integral test. In other words, they are all decreasing and they are all positive functions. So you just have to apply the integral test. It'll force you to do integration by substitution in one of the 3 cases. The rest of them are easy, I hope. I did not bring my mug today, but if I had, it would have helped you with one of these. So hopefully you know what I mean by that. There is going to be a hard tangent. Okay. 2, and then 1 more. There you go. 1, 2, 3, 4. That's all. Oh, you save this for whoever's not here. Should put this on the screen, I just realized. All right, let's see how we're doing. If you're done, feel free to pass your paper over. If you're still working, it's okay. Let's see what we have here. Very nice. Oh, you want to look at it again? You don't want to. I don't want to? Why not? You gotta move it. Excellent. Got some integrals. You don't like your integrals? Nope. Not too bad. Yeah, so at the very least, put down an integral. Then at least I'll think that you know what you're doing, even if you don't want to finish the integral. So give it a go here. Some of them may be more obvious than others when you do your integral. Where's my thing? There it is. All right, so if you're still working, try to wrap up that last of the 3 integrals. I'm sure you're just doing the last one. It's kind of a pain, the substitution. So you can always just take a guess and say, yes, it either converges or diverges, and maybe you'll be right. You're all set. Excellent. Coming out of the woodwork here now. go like that and then I'll come back. Give you guys minutes. Oh, you're on. Coming back up. Good job, good job. You've got anti-derivatives. Okay. So, yeah, so you know that that's just going to tell you whether it's going to make you better. You know, these parts of that. But you got integral. Converges and diverges. Daniel took a guess, did you? Educated guess. Good job. Excellent. Well done. All right, good. Anyone else? Do I have them all? Holding out on me over here. See, so you've got some guesses. Maybe you got them right. Nice work. Excellent. I like it. Okay, so I think I've got them all now. Anyone else? No. Let me staple so that I can keep them together in my backpack. Done. Okay, so here it is. Here's my first one. So my first one, I actually went through, I thought I should at least show you what it means to check if you can use the integral test. So I checked the function is greater than 0 because x will always be bigger than 1. So this number will be bigger than 0. I did the derivative, and you'll notice that no matter what you plug in here, even positive or negative, but we're dealing with positive numbers, this will always be negative. So we're good. We can use the integral test. Here's the integral test. I do the integral over that range. Technically, I should do a substitution, but we've done this so many times. Hopefully, it's okay to just write it like this. 2 over this is going to be 2 times the natural log of that. And when I do the limit as x approaches infinity of that, I do get infinity. So that diverges. So there's number 1. Okay, let's take a look at number 2. This is the arctangent one. So here's my work. I did this. Like I said, I thought I should do it. This is obviously greater than 0 no matter what you plug in here for x. The derivative is this. And this, as long as x is positive, this will be negative. So we're good. That is to say, this is a positive function that is decreasing. Well, going that way, decreasing. Then I did the antiderivative. I kind of hinted. I didn't have my mug here, but my mug has printed on it that the derivative of arctangent is this. So this is the antiderivative. And then I just have to think to myself, what is the limit as x approaches infinity of the arctangent of x? And if you don't know, you could just take your calculator and plug in large numbers for x. So I do arctangent of 1 million, arctangent of 1 billion, arctangent of 10 to the 100th, and you find that you get closer and closer to pi over 2. And the arctangent of 1 is pi over 4. I know that one we all know, but so that's what I end up getting is pi over 2 minus pi over 4, which the total is pi over 4, or after you subtract. So this thing definitely converges. Because the integral converges, the sum up there will converge. Finally, the third one, and I realized pretty quickly that I have a typo, but I didn't start this until you had already, some of you finished, so sorry about that. So actually, it works maybe to your favor because it was pretty easy because there was a typo. Anyway, I checked. The function value is positive for all positive values of n. I guess as long as n is bigger than 0, because n equals 0, you get 0. But anyway, that's positive. And then the derivative, it turns out the derivative is also positive. So I did the derivative. The derivative is non-negative. So technically, I'm not allowed to use the integral test. However, I told you verbally that it was derivative, that everything was good. So you did the derivative test. So technically, I would have to stop here, and I would have to use some other method. But this one does diverge. Go back here. Let's see, why is that like that? Wait, I never did it? Oh, I never did it. Yeah, so I guess I was like, oh, I'm not going to do it. But if you do this integral, 4x e to the 0.5 x squared from 0 to infinity, this diverges. You might wonder, what is that one? Okay, I'll show you. So this will be this 4e to the 0.5 x squared evaluated from 0 to infinity. So it's the infinity that's the problem. When you put infinity into here, yeah, it's too big. It blows up. So the limit as x approaches infinity is infinity, so this one diverges. Okay, so what we're doing today is we're going to start this series flow chart. And we will hopefully get at least the beginnings of it. So here's the deal, the start. Here, I'll put an example over here, what I mean by start. You have a series like this. And the question is, does this converge? So that's the big question. Does that converge? And this flowchart will help us to determine that. So we start. At the start, we have two series that are going to be our sort of gold standard series. So let me write them down. The first one is the geometric series. So I'll put this, I don't know, am I supposed to put a diamond here for a question? Why not? So, is that what we do? It doesn't matter. Geometric. Question mark. And there's either a yes or there's a no. Do I have that right? It's a diamond? I don't know. I should know, but whatever. It doesn't matter. Whatever shape you want to put there, you want to put an oval there, I don't care. The point is that as you are thinking about a series, if you have a series here, and you want to know, does this converge or diverge, then you're going to go through this set of questions, and they will help you to determine if this converges or diverges. So you start and you say, is your series, is it geometric? Here's what you would be looking at if you would say yes. That is a geometric series. So is it a geometric series? So there's either yes or no. And then if it is, I guess I'll make another one of these. So we have the sum of r to the n. And the question is r less than 1? And this is the one where the absolute value, where it matters. And so if it is yes, then you converge. And if it is not, hold on a minute. I don't want that there. I'll put it here. No, then you diverge. So this is old stuff. This is old stuff. You're used to this. So just as an example, let's just pretend we're using this flow chart with that series, and I'll pick one more just for fun. So here n goes from 3 to infinity of -4/3 to the n. Okay, so let's deal with these two. They aren't too bad. Let me find my volunteer list. Ooh, I've got to fix this. I'll just fix it now. Okay, where's the volunteers? Randomize. Ryan, you know the first one. Does that one converge or diverge?
Converge.
Converges because 3/7 is between -1 and 1. Very good. So that one will converge according to that. And then we get to this one and we're like, does this converge or diverge? Well, it happens to be a geometric series, so we can use this rule. So who is it? Andrew? Andrew, do you know it? Does this converge or diverge? Why does it diverge?
Greater than the absolute value.
Yeah, so the 4/3 is bigger than 1. So very nice. So that one diverges. So very good. So we've got this taken care of. That's the start. The second of our gold standards for series is going to be the p-series. So let's go down. The next one is it a p-series? Make this a little bigger. P-series, question mark. Oh, go away. Okay, sorry. Siri keeps popping up. Look, she's up there again. Go away. At least I've silenced her, so she isn't. It used to be that every time I taught this lesson, she would pop, can I help you with something? I don't understand your question. And I'm like, wasn't a question. Okay, so P, this thing. Okay, so if this is a P series, then the question that you're going to ask is P greater than 1, question mark. I'll show you examples just so that you understand. And if the answer to P is greater than 1 is yes, then you converge. Converge, good enough. And if the answer is no, then you diverge. So far, so good? Now, honestly, the next thing I'm going to write is not what I would normally do when I was doing a test to see if series converged. I just realized, what is missing? Did I skip a section? Yeah?
Isn't there an alternative when P is less than or equal to, or is that already, oh no, it's already covered, because you're just looking for.
Yeah, it's either yes or no.
Yeah.
Is there an arithmetic series?
No, we don't care about them. Well, arithmetic series always diverge because they're, if you're adding them up, really, because you're getting bigger. And even if you go negative, you're getting, yeah, it's the same problem. So yeah, we don't worry about those. Those, by the way, these are the two biggies, those two, geometric and p-series. Everything we do, almost everything we do from here on out, we're going to refer back to one of those, literally. But before we do, I feel like there's the nth, just a minute. Let me mention this. I feel like this, did this get skipped over? That's terrible. Sorry, I have to redo that. Here. Let's do it this. Let's do this. Is the limit as n approaches infinity of a sub n equal to 0? Okay, so I don't have any recollection of doing this. But this is important. I'll dig it out because, like I said, the homework today is not due till Wednesday. We only have 4 minutes, so we're in good shape. But yeah, I'll figure out. If we need to, we'll go over this tomorrow. This is called the test for divergence. It's a weird test. So anyway, is the limit equal to 0? Okay, well, oh, go away. So here are the answers. Here, let's see, I'll put a no here. So this one is a little bit weird. So I'll explain this one briefly. Okay, so let me explain that, because that's weird. So here, let's do this. The sum. Let's do an arithmetic sequence. So let's take a look at that arithmetic sequence. Does that converge or diverge? And the answer is that because what you're adding together, 3 plus 2n, never gets small, what makes these series converge is that the terms get smaller and smaller, closer to 0. So if you're always adding together numbers that are not close to 0, you will never converge. You'll always keep growing, even though you might be growing slowly. This one actually grows quite quickly. And so 3 plus 2n goes to infinity, so the answer is no, because you're adding together bigger and bigger things. Let's say I add together this. Let's try this. N plus, let's do n minus 1. But n minus 1 over n plus 1. So that series, n goes from 1 to infinity. So let's say I added these numbers together. Then what am I going to be doing? I'm going to be adding 0 over 2 plus 1 over 3 plus 2 over 4. You see the pattern now probably, and then plus a bunch of dots. So does that converge or diverge? Well, I can tell you right now that this will diverge. And the reason is that I keep adding together numbers that get closer to 1. Notice that as n gets big, this fraction, so it's like you're adding together a bunch of ones. And if you add 1 plus 1 plus 1, you're never going to converge to anything. So that will diverge as well. So that's what this refers to. So I should stick that in there somewhere. I don't know why we haven't done it. I'll try to figure out where it belongs. So we'll go over it tomorrow. But what we were supposed to do today is this next one, and that is the comparison tests. And so that's what's next, is we're going to do comparisons. Compare. Compare, question mark? Can we compare? Well, if you can compare, then it's powerful to be able to compare. What I mean by compare is, am I going to be able to compare my series to one of the series that I know converges? So for example, if I'm doing this, 1 over 2 to the n, that converges. What about this, 1 over 2 to the n plus 1? Notice that all I've done is I've taken that and I've added 1 to the denominator. Will this converge? And it turns out, we'll show why tomorrow, it turns out that because this one converges, it shares some of its glory with this one, and this one will converge as well. So they both converge. But we'll explain why that is tomorrow. So comparison tests, what we're going to do is we're going to compare with these two. Those are the things that we always compare ourselves to because we know about them. Okay, I'm going to stop the recording. The homework, I haven't even got it up online, but it won't be due until Wednesday, and it will be about comparison tests.